Hey everybody, welcome to the first video on the photoelectric effect. So here is a second phenomenon where people did some experiments, they made some observations, but they couldn't explain the results and observations using the wave model of light, similar to what happened with thermal radiation. But lo and behold, the photon model of light explained everything that they were seeing. So we'll talk about the photoelectric effect, how that happens, how the photon model can explain the observations. We'll also look at an application of the photoelectric effect, the photomultiplier too, in another video. So let's talk about the photoelectric effect first. What is it? So under the right conditions, if you have light hitting a piece of metal, electrons can be ejected. That's the photoelectric effect. So you have a piece of metal here, you have light coming down, and again, under the right conditions, you can have electrons. That's my symbol for an electron, E with a little minus superscript, popping off. These are sometimes referred to as the photoelectrons. Now, in a controlled experiment, what typically is done, let me show you. I'm going to go to the summary notes. I have a diagram here, and you can see it right there. I'll make it a little bit bigger. So this is a typical setup that you would find. Because electrons are flying around, we have to do this in an evacuated tube. So that's what you see here, that gray thing. So that's a glass tube that's been evacuated. And inside there, you have a metal plate right here, the emitter plate. And you can see the light coming down and hitting the emitter plate. Photoelectrons are ejected, but they can be collected. They can be sent towards this other plate, the collector plate, and you can make this part of a circuit, as you see right here. So you can see the collector plate is connected, in this case, to the negative terminal of the battery, and the emitter plate is connected to the positive terminal. There is an ammeter here, so you can actually measure the current that flows from these photoelectrons, caused by these photoelectrons. All right, and this is no big deal, but we might as well point it out. In this diagram, you can see that the electrons would be going counterclockwise, but our convention for current is that the current is the direction of positive charge flow, so the current arrow is going clockwise. Now, what can you vary in the experiment? Okay, so you can vary the intensity of the light. You can also vary the frequency of the light, right? And you can measure current, but you can also vary this voltage difference supplied by the battery. You can vary the polarity, so you can switch the terminals, and you can also control the size of the voltage difference. So if you look right now at this polarity, you'll see that the emitter plate is connected, like I said, to the positive terminal, and the collector plate to the negative. So positive terminal means this is a higher voltage than the negative terminal end. So the emitter plate right now is at a higher voltage than the collector plate. And the voltage difference between there, right, is going to affect the motion of the electrons. Now, if you remember, electrons are negatively charged particles. They will speed up going from low to high voltage. So in this configuration, they're going to be slowed down by this voltage difference. There's an electric field that points to the left from the emitter plate to the collector plate. That electric field exerts an electric force on the electrons in the opposite direction since they're negatively charged. And that braking force is going to slow down these electrons. So one of the things that's done in a typical experiment is, with this polarity of voltage difference, you increase the voltage or the potential difference until you have no current on your ammeter. That value of voltage difference or potential difference is called the stopping potential. And what's happening physically is that when the light hits this plate, electrons are being ejected with a variety of kinetic energies. Some electrons are coming off faster than others. The maximum kinetic energy that this electron is going to have, right? There's going to be some maximum. If you stop that maximum kinetic energy electron, that fastest ejected electron, that's when that current's going to hit zero. So the stopping potential is going to be stopping the electron that's ejected with the maximum kinetic energy, and the electrons that are ejected with the maximum kinetic energy. Okay? All right, so let's work out what should happen in the wave model of light for certain observations. Okay, so the first observation, and I'm going to the quantum physics study questions because there are 4 observations that you should know about, and you should know what the observations are, why the wave model fails to explain them, and why the photon model is successful. In this video, we'll just focus on why the wave model can explain them, and in the next video, we'll actually develop the photon model's explanation of what's happening and see why the photon model successfully explains these observations. Okay, so the first observation is for frequencies, for frequencies below a certain cutoff frequency, no photoelectrons are seen. So what we mean by that is, if you change the frequency of this light, if you get the frequency of the light too low, below what we call a cutoff, you don't see any current at all. There are no photoelectrons being ejected. Doesn't matter what potential you have here. In fact, you can even flip the polarity on the battery. So now you should be speeding up electrons if any are ejected. And you don't see any current if you are below a certain frequency, the so-called cutoff frequency. And this is independent of light intensity up to a certain point. If you start blasting this emitter plate with a huge intensity and start heating it up significantly, you're going to be ejecting some electrons just thermally. But under reasonable intensities, even if you increase the intensity, you don't see any photoelectrons if the light is below a certain cutoff frequency. Okay, so that doesn't make sense in the wave model because frequency, right, is not the only thing that's determining the energy carried by the wave. It's also the amplitude. So it would seem that if you do crank up the amplitude and do crank up the intensity, that the electron should be able to absorb enough energy from the wave that they can break bonds and be ejected. They're going to have to break some electric bonds to get ejected. And these are going to be outer shell electrons, right, on these big metal atoms. They're going to be electrons that can easily shift around, so-called conduction electrons, can easily move around. They're not tightly bound to any individual atom. So they should be able to absorb enough energy from the wave at even a frequency that's relatively low, provided there's enough intensity, and be ejected. But that doesn't happen. So that's a strange one. What's another phenomenon that we see? The stopping potential, and therefore the maximum kinetic energy of the photoelectron, is independent of the light intensity. Okay, so let's talk a little bit about that. And let's specifically relate the stopping potential to the maximum kinetic energy. I'm going to go to my notepad just to sketch some things. This harkens back to physics too. So if you remember in my diagram, I have the emitter right here in that picture on the study notes, and my collector over here. And the light is hitting the emitter. Now, the electron is going to be ejected. And again, it's going to be, these electrons are going to be ejected with a range of kinetic energies. If the electron makes a clean break, right, it doesn't lose any energy in collisions. It just breaks the bonds and is ejected. That's going to be the maximum kinetic energy. So there's going to be some electrons that have a maximum kinetic energy as they're ejected. You are slowing down these electrons, right? So you're slowing down these electrons with this polarity of the voltage. So when the fastest moving electrons, the ones with the maximum kinetic energy, just arrive at the collector plate with a final kinetic energy of 0, that's when you have stopped the current. Okay, that's your stopping potential difference. So the difference between these plates we'll write as V sub S. Okay, so really what we're going to do then is, if we go back to physics 2, remember when we were accelerating particles between plates, we said that the change in the kinetic energy, absolute value, is for this charged particle, typically it's an electron, is the absolute value of the charge times the absolute value of the voltage difference between the plates. Okay? So what's the change in the kinetic energy that we're interested in? Well, the initial kinetic energy is this maximum, K max, and we're interested in where the final kinetic energy is 0. So the change in the kinetic energy is just going to equal K max, the absolute value of the change, right? And the fundamental charge, that's just E, right? Because the absolute value of the charge of the electron is the fundamental charge, 1.6 times 10 to the minus 19 coulombs. And our shorthand for the absolute value of the voltage difference is just this stopping potential or stopping voltage. So the maximum kinetic energy is directly proportional to the stopping potential through the fundamental charge. Okay, so what observation 2 says is that this maximum kinetic energy, or this stopping potential, because in the experiment, what you're directly measuring is the potential difference across the terminals of that battery. So you're going to be measuring the stopping potential directly. Well, it turns out that is independent of light intensity. Now, that does not make sense in the wave model of light because, as we said before, right, if I crank up the intensity of this light, it seems like the electrons should be able to absorb more energy per unit time. So it seems like if I crank up this intensity, the maximum kinetic energy that an electron can have should increase. So if I crank up the intensity, I should be ejecting some electrons with more kinetic energy. It seems like this stopping potential should also increase. But you don't see that. So even if you crank up the light intensity, now this is for light at one frequency. Okay, so you're not changing the frequency, but if you increase the light intensity, you don't see an increase in stopping potential. Or if you decrease the light intensity, you don't see a decrease. So this stopping potential is independent of light intensity. Okay? It's quite interesting to see that, because again, the wave model of light doesn't support that. Okay. The next thing. A plot of stopping potential versus frequency is linear. It's the linear part that we're emphasizing. So what that means is we do this experiment, right? If we change the frequency and measure the stopping potentials. So again, at one frequency, the stopping potential is a constant. It doesn't vary with light intensity. But if we change the frequency, we will change the stopping potential. And in fact, it looks like this. And if you do the experiment over a certain frequency range and you measure the stopping potential, you end up with something like this. It is in fact linear, and this is that cutoff frequency. I'm going to call it F sub CO. Remember, we made the observation that for a given metal, there is this cutoff frequency below which there just aren't any photoelectrons, so there's no stopping potential because there aren't any photoelectrons being ejected. And if you increase the frequency beyond the cutoff frequency, you find out that there is this linear increase in stopping potential. Now, the wave model of light, you could argue that if you increase the frequency, yes, then you do increase the power delivered by the wave. You do increase the intensity, therefore, of the wave, power per area. And it does make sense that an electron should be able to absorb more energy from the wave and come off faster. So you would expect the stopping potential, you could argue the stopping potential should increase. But there's no justification for a linear increase. That's what that doesn't jive with the wave model of light. Why this nice straight line? Okay? All right, so we'll come back and explain why it should be linear in the photon model. But there's one more observation that you can make. This one is a little bit more sophisticated equipment, but if you have the equipment where you can look and see how fast does it take to actually collect the first electrons after you expose this metal to light, it turns out that these photoelectrons are emitted in an extremely short time. So the photoelectric process is occurring very quickly, even in extremely low light intensities. And that's the caveat. So if you're barely illuminating this metal, you still have photoelectrons being ejected very quickly, right? And if you crank up the intensity, that time for the first photoelectrons to be emitted is essentially the same. So even in very low light intensities, this is occurring very quickly. From the wave model, that doesn't quite make sense, because if I crank down my intensity so it's extremely low, it seems like it should take the electrons more time to absorb energy from this really low intensity wave to get enough energy to break bonds and then be ejected. So that doesn't seem to make sense either. Okay, so what I want to do in this video again is establish what is the photoelectric effect. So we did that, right? That's when light hits a metal and under the right conditions, electrons are ejected. We also wanted to explain what a typical experiment looks like, as you see in this figure, introduce the idea of the stopping potential, and also talk about these observations. Okay, this plot, for instance, why it's linear, why do we see photoelectrons being ejected so quickly, even in low light levels. The first observation that there is this cutoff frequency. Below a certain frequency, we don't see photoelectrons, right? And how come the stopping potential for a given frequency is independent of light intensity? All right, now, again, next video, we'll see how the photon model explains all of this. Okay, so cue up the next video. Bye-bye.